Maximum and minimum values, Part A. Motivation. Optimization problems appear in many applications. Their solutions usually hinges upon finding extreme values of functions. We want you to remember derivatives and their association with the increasing and decreasing nature of a function. We want to understand how extreme values of a function on closed interval occur either on the endpoints or at the critical numbers. Optimization problems have a lot of nice applications when you want to find maximum profit, when you want to find the best size of the screen for your smartphone. All this will show up on some local or global maximum or minimum of the function. And that's why we'll be learning how to locate those points. Definition. A function f defined on an interval ab, closed interval, has a local or relative maximum at c in ab, open subinterval, if there is a h, positive h, and an interval c minus h, c plus h contained in ab, such that for every x in this interval, f of c is greater or equal f of x.
Why do we need this h?
This h plays a role of a little step. So we're stepping away to the left and to the right. I can introduce it here in the picture. If we are having a closed interval a and b, and we're finding a point c, which is located in the open interval a and b, we're making a little step to the left. So I want to have c minus h, to the right c plus h. In this interval, if f of c is always bigger than all other points, bigger or equal, then it's going to be a local maximum. It might look something like this. I might have several things and then go down, up. You see here, it might be not the smallest point in general, but locally it is.
Okay.
And that's why we do not look at critical point, at the local maximum, local minimum, at the endpoints A and B. We only look at them in the open interval, because we cannot have step to the left and step to the right at the endpoints. Okay. In short, the largest value f takes on near x equals c is f of c. And this is going to be the smallest number or the biggest number. In this case, we're talking about local maximum. So the biggest number, but locally. Same definition for the almost same definition for the local minimum. A function f defined on the closed interval a and b has a local minimum, a relative minimum, at the point c in open interval ab if there is a small positive h that creates an interval c minus h, c plus h in the initial interval ab, such that for every x in this interval, step to the left, step to the right, c minus h, c plus h, f of c is the smallest number, less or equal than f of x. Basically, we're saying that the smallest value f takes on near x equals c is f of c, the smallest one. The definition says that we might have a local maximum and local minimum here, but here's a nice question. Do you think we can have only unique local maximum, local minimum, or we can have many?
We could have many, right?
We might have many, and that's exactly good. We even have a lot of examples, and we're going to look at one example soon. And in this case, we can call maxima, so many, or minima, many, at more than one input value on a closed interval. Do you remember there is a function that looks like a wave, has a lot of oscillations? What does it look like?
Oh, it's the sine function.
Sine function, yes, exactly, good. That function has infinite numbers of local minimum, local minima, and local maxima. Here's a nice example. So, interesting to point out that the same will happen for the open or semi-closed intervals. Here's a nice example. F of x equals sine of 1 over x. Just like I mentioned, tricks, sine and cosine, they have infinite many local minimum, local maximum again and again and again and again. Well, this one has infinitely many local maxima and infinite many local minima on the semi-closed interval 0, 1. We cannot include 0. Do you see why?
Because it's the parentheses.
Oh, yeah, but what do you see about the function over
because
here?
you can't divide by 0.
We cannot include 0 here. It's sine of 1 over x. Good job. Yes. Let's see what's going on here. So f here takes on its maximum value and gonna gives you 1 all the time. If I plug 1 over pi over 2, which is 2 over pi, why? Because then I will have sine of 1 over 2 over pi, sine of 1 over 2 over pi, which is sine of pi over 2, which is, do you remember?
1.
Which is 1. Good. Which is 1. Same happens with 1 over 5 pi over 2, which is 2 over 5 pi. Same happens so on and so on, infinitely many. I can generalize this result as 2k plus 1, 1 over 2k plus 1 times pi over 2, which can be rewritten as 2 over 2k plus 1 times pi. For any even positive integer k, we have infinitely many local minima and local maxima here, and it is 1. Same with minima, but different inputs. Here we can have that, we can say that we have infinitely number of minima, and it's going to be -1 at, if I remember 3 pi over 2, right, gives me -1. So 1 over 3 pi over 2, which is 2 over 3 pi, 1 over 7 pi over 2, which is 2 over 7 pi, and so on. We can say that we just have 1 over 2k plus 1 times pi over 2, or it is 2 over 2k plus 1 pi, but here k is odd positive integer. This is a very interesting example because, as I mentioned, we have infinitely many points where we are having local maximum, local minimum, but on a very small interval from 0 to 1. This is a pretty rare case, and you're probably not going to see it again, but if you remember, the function oscillates more and more and more on a very small interval from 0 to 1. Very interesting example that shows you that you should not expect that nothing going to happen on a short interval. Everything can happen there. Infinitely many points that have local maximum, local minimum. Let's look at one example here, which is the function is defined on a closed interval from -3 to 2. You kind of can have some intuition from the graph that you see some local hills, local pits that might kind of show you, oh, there might be some local minimum and local maximum here. Can you guess? Can you have some intuition in this case?
At x equals -2 and x equals 1.
1. And what do you think happens at -2?
It's going to be a local maxima.
It looks like local maximum, yes. And at 1?
A local minima.
Local minimum. There are many ways to identify those points. And first, we just introduce some intuition numerically. We're going to provide you with a table. Here's a table to show you what is going on around the point -2. As you remember, we are having an interval with a step to the left and step to the right. -2 minus h and -2 plus h. And h is some small positive number. So everything that is on the left from 2, not everything, but just some small random numbers, they are more or less close to -2. Gives you 21.14, 21.62, 21.91, which is getting closer to 22. But the main point is that 22 is still bigger. And that's important to understand. The moment we stepped away to the right, what's going on here? Now we have numbers that are smaller than 22, again to the right. 21.91, 21.66, 21.24. So we can say that f of negative 2 is greater than or equal to f of x for every x near negative 2. Of course, we could not check all x here. It's just a table with 6 numbers there around negative 2. That means that for every x between negative 2 and negative h and negative 2 plus h, all the numbers are smaller than 22, then f of c, if you remember that c, we found that c. Here it is. So this is exactly, your intuition was correct, and this indicates local maximum. Also, we can check what's going on around 1. So first we can say, indeed, f has a local maximum at negative 2. Again, we did not check all the points. It's impossible to do numerically to check all the points. But right after this, we'll figure out how to justify that there is a local maximum, local minimum. A little bit more numbers for a point x equals 1. Again, what's going on? Now you tell me what's going on the left. On the left, when it's 1 minus h, and then 1 plus h.
So on the left, the numbers are bigger than negative 5. And on the right, they're also bigger than negative 5.
Yes, exactly. On the left and on the right, they're all bigger than negative 5. Negative 5 is the smallest number. So c is 1. F of c is negative 5, the smallest number here. F of 1 is less than or equal to f of x for every x near 1. Near means in that interval for x between 1 minus h, 1 plus h, where h is just a small step away, a small positive number. Here we can say that f has a local minimum at 1. Let's introduce a very important theorem, Fermat's theorem. Fermat's theorem will help us to identify those points where we can find local maximum, local minimum. The theorem says if f has a local maximum or minimum at x equals c, then the derivative of the function at that point either does not exist or 0. And this is a very important, helpful tool, because basically I'm telling you where to look. There can be infinitely many local maxima and local minima. Will you look at all the points? No, you just need to look at those points where the derivative either does not exist or 0. Basically, like I'm saying you, all those points will be red, so you don't have to check all the other colors, just red ones. And then you can check each of those. So now remember, we need to, every time, we just need to find derivative and check if the derivative exists at the point or 0. Then we can try to see, do we have a local minimum or local maximum, because this is still will be a question. But we don't have to check any other points anymore, and that's good. Here's an example. The function is given, if we remember this function from negative 3 and 2, remember the graph, and we had the graph. So let's check if it's true or not. The derivative is 6x squared, remember, from 2x cubed, plus 3x squared gives me 6x, and negative 12x.
Negative 12.
And plus 2 gives you 0. Taking derivative, and then remember the graph, which we claimed that negative 2 was a local maximum. So now I'm going to plug negative 2 into my derivative, and I expect to get 0. Let's see. Derivative of the function at the point negative 2 gives me 6 times 4, because it's negative 2 squared, plus 6 times negative 2, minus 12. And indeed, 6 times 4 is what?
24.
24. 6 times negative 2?
Negative 12.
Negative 12, which gives you 24 minus 12 minus 12 is 0. But what does it mean? I just want to make sure. Do you remember? What does it mean to have a 0 derivative at this point?
There's a tangent line horizontal to the graph at that point.
Yes, good. So tangent line, when taking derivative, we're talking about the slope of the tangent line. When it's 0, it shows some kind of behavior. The positive means growing, the function is increasing, the negative, the function is decreasing. 0 means horizontal. So it's indeed what's happening here. We're climbing the mountain and my slope is increasing, slope of the tangent line, increasing. Then it's positive, then becomes 0. and then becomes negative, 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 negative. So indeed, at this point, derivative is 0, which means that the slope of the tangent line is horizontal. And that's what gives you, that's where this intuition is coming from. When you look at the graph, you can see, oh yes, there's a hill, but what else do you see? There is a horizontal tangent line. Same with the minimum. You can see, oh, there's kind of a pit over there. It looks like it's a local minimum. But the idea is still the same. What you see is a horizontal tangent line at that point. Let's check. So we have a derivative. Let's plug a new next point, 1. At the previous point, we did have a local minimum and local maximum. Now we're having a local minimum at 1. F of 1 is 6 times 1 squared, which is 6 times 1, plus 6 times 1, minus 12, 6 plus 6, 12, minus 12 is 0. So indeed, it's always going to work. The local maximum, local minimum points will give you 0 derivative, or derivative might not exist there. Let's define those type of points. They are very important, and since we're going to be using them all the time, let's name them somehow. And it's a very, I guess, natural way to name them, critical numbers, because the critical, something is important is happening there. So we're defining f, function defined on the closed interval ab. C will be a critical number on the open interval ab, critical number of the function if derivative is 0, or do you remember the second one?
If the tangent line is horizontal.
This is the one. This is the 0 one. And the second one does not exist at all.
Does not exist.
2 cases. You will get used to it with time. And that's what we will have to check all the time. And I ask you because most of the students forget to check the does not exist part. Zeros, kind of, they always there. You want to solve for x, you found correct equation, something like this. But usually students forget to check the points at which the derivative does not exist. So I will be pointing this out all the time. 0 and does not exist. That gives us critical number. Some people call it Cn. You will see it sometimes critical number. This means that the function can only have a local extreme value, local minimum or local maximum, at the critical number. So we gave it those points a name. We don't have to check all of them. Just find critical numbers. From infinitely many numbers, you can have only 2 or 1 critical number, and then you check is it local maximum, local minimum, or nothing. But you don't have to check others. And that's why it's such an important tool. Now, example. 2x cubed minus 24x plus 5 is defined for all real numbers. Find its critical numbers. Let's take a derivative first. Let me ask you. Let's take a derivative first. What is a derivative of 2x cubed minus 24x plus 5?
So you're going to have 6x squared minus 24.
Yeah, good job. Minus 24. And I have it here. The derivative of the function is 6x squared minus 24, and it's defined everywhere. And that's an important step. So we're not saying it's just to add some words. If you remember, we need to check where is my derivative is 0 and does not exist. If this function defined everywhere, then we don't have to check does not exist part anymore. So we just need to check where, at what points this derivative will be 0. Let's do it. Basically, we are solving an equation. We want to say, oh, the derivative should be 0. Let's solve for x, which means 6x squared minus 24 equals 0. Solving for x. You can factor out 6 here, and you have x squared minus 4 times 6 gives you 0. You don't have, so 6 is not 0, but then x squared minus 4 should be 0. And what solutions do you have from here?
Positive and negative 2.
Good. X squared is 4. X squared is 4. And x will be plus or minus 2. Yeah? Square root of 4. Good. So we have 2 points here. And again, so usually after this, you check at what points your derivative does not exist, but is defined everywhere. So we don't do that. Here we have critical numbers of the function, two of them, plus and minus 2. Here's the graph. And indeed, as you can see, what is going on at -2 and what is going on at 2? What do you see?
There's a local maxima at -2 and then a local minimum at x equals 2.
Yeah, exactly. So theory works. But again, we kind of did not justify why there's a local maximum there, why is there a local minimum. This is going to be next step. We will learn it soon. But first, we just want to make sure that the first step in order to find local extrema is to find critical numbers. Both critical numbers, plus and minus 2, correspond to local extreme values. Next example. Here we are having a function x minus 4 raised to the 2/3, and it's defined everywhere. And the first step, as always, is to take a derivative. I will help you a little bit, maybe not to jump to the next step so fast, but if this is my function, when I'm taking derivative, what would you say first?
So you're going to have negative...
First, this, look at it, 2/3.
Oh, yeah. 2/3 times x minus 4 to the -1/3.
X to the -4. How did you get -1/3 though?
So 2/3 minus 3/3.
Yes, exactly. 2/3 minus 1, and you always think, okay, I need to have common denominator. So really fast, in your head, you just imagine 2/3 minus 3/3, which gives you -1/3. -1/3. Agree?
Yep.
Good. 2/3 times x minus 4 raised to the -1/3. You can rewrite this as 2/3 and then x minus 4 over x minus 4 raised to the 1/3. Well, what we're doing here, remember we want to find zeros, means we want to set it equal to 0 and solve for x. And we want to check where the function does not, when the derivative does not exist. So here you look at the denominator and you can immediately say that
4.
4 is that number.
Yeah.
It does not exist when x is 4. So the derivative defined only for all x but 4. So this is going to be a critical number. It's coming right away from this. That's why we decided to rewrite it, because when you have a fraction, you can see, you look at the denominator and immediately you can say, oh, we don't want to have zeros in denominator. Those points gives you critical numbers. To find zeros, you look at the numerator, because only numerator, when it's 0, can give you zeros. But numerator has 2. Can 2 be 0?
No.
So there is no points there. Equation derivative of f equals 0 has no solution, because numerator is just 2. Doesn't give us any solution for x. So we can say we have only one critical number here, and it's 4. And this time it's coming from the second part, then the part where the derivative does not exist. Here's the graph. You see, even though the function is continuous, the derivative for this point does not exist because of this shape. And we remember the corners and those kind of shapes when you don't have derivatives.
It forms a cusp,
Cusp,
right?
yes, cusp.
Okay.
I always forget this word, cusp, exactly. Corners, cusps, and we don't have derivative there. So that's why we got this undefined derivative at the point, and it's the only critical number we have here. The only critical number corresponds to local maximum or minimum.
This one would respond to the local minimum.
Minimum, the smallest number locally, you see? I don't know what's going on after this, after whatever I see on the graph, but I know that here, locally, it is a local minimum. Which is not enough. Not all critical numbers correspond to any extreme values at all. It gives us a chance to have a list of numbers to check. But some of them might not give you any maximum, any minimum, nothing. So we need to have some new tool in the future to check, is it local maximum, is it local minimum, what is going on there, to check the behavior at the critical number. The function, here's a nice example. It's a cubic function, x to the third power is defined everywhere. Let's try to find critical numbers here. What is the derivative of x cubed?
3x squared.
3x squared. And it's defined everywhere. So again, we want to check two things, zeros and where the derivative is not defined. Well, it's 0 at 0. That's the easy one. It's 0 at 0. And then we can say that this is a critical number. Will this number give us any local minimum or local maximum? Let's see from the, I will draw the graph in a second, but it is actually an inflection point. So we should be careful with conclusions. It is a critical number, but it's just changed the behavior of the function, which was, the function was increasing, stopped for a second, and it was keep increasing, increasing, indicating an inflection point here. Not a local minimum, not a local maximum at all. The function h is monotone increasing everywhere and has no local or absolute extreme values. Just keep increasing. Let's do a couple more examples to learn, to practice how to find critical numbers. And we'll have different cases here. And this example is good because it includes both cases. So steps, let's kind of remember some ideas here. Step 1, take a derivative. Good. So step 1, let's take a derivative. What is the derivative of this function?
So we're going to have 12 over 3.
Oh, yes, good. 6 times 2/3, right?
Yes.
12 over 3.
Times x.
X to
the
the
negative 1/3.
So 2/3 minus 3/3, and you say it's negative 1/3. Exactly. Good. Negative 1/3 plus.
And then we're going to have plus 5/3.
5/3
times x.
to the
Negative.
the 5/3 minus
3/3.
3/3 gives you
2/3.
2/3. Yeah, good. 2/3. That's how you do it. So you don't have to do it fast. You can always write down a small cheat sheet over there in the corner to check everything, all the calculations. Here it is. So this is my derivative. And my goal is to find zeros and find when the derivative does not exist. Usually, it's a very good suggestion to factor something out. If you see you can factor something, do it. And what we're doing here, we want to notice, so I want you to notice, we have x everywhere, remember? Usually if you have something like x squared plus x cubed, you factor x, right, with the lowest exponent. So in this case, I want you to do the same thing, but you first need to figure out what is the lowest exponent here. I want you to factor x to what?
The negative 1/3.
That's the smallest one, indeed. Good. Yes, exactly. What is going to stay? So factoring means dividing it. And what is going to stay there instead of the whole term? What is 12 over 3, by the way?
It's 4.
4. Yeah, let's just write it as a 4. So what is going to stay there?
4.
4 times 1, right? Disappeared.
Yep.
Good. Plus, what about the second term?
So 5/3.
5/3.
And then
Then x. So how do you do it? You can again have a cheat sheet somewhere to write down x 2/3, and then you do minus. This is what you're factoring out, x to the negative 1/3. Then you use the properties with the division x to and x with the same exponents. So I can just do 2/3 minus negative 1/3, which is x to 2/3 plus 1/3.
1.
Which is 1. Yes, exactly. 1. Good. Figure it out. You need to be really tedious here not to make any mistakes, but after all, it works. Again, what we keep doing here, I would recommend to rewrite this expression as a fraction if you can. And then you will see numerator and denominator, and that's very helpful to see what is going on at the bottom of the fraction, what is going on at the top of the fraction. And we can make a fraction here because I can see this x to the negative 1/3. What is going to be in the numerator?
4 plus 5/3 times x.
Times x, and denominator?
X to the 1/3.
Yes, good, exactly. X to the 1/3. So now you see two sides of the fraction, and it's helpful because now you can analyze the situation. The idea is I want to find zeros and the points at which derivative does not exist. Zeros, which means where the whole fraction is 0, are coming from the numerator. So you check at step 1, you want to check, for example, first the top. and solve it for x. The points that make the derivative undefined, they are coming from the denominator. And that's how usually you do it. You check both sides and you don't forget about the bottom. You don't forget about denominator. Usually students do. So try to do both, always. Check both. Let's do step by step. Step 1 and step 2. And this is a second step of the whole idea. The first step, take a derivative. Simplify it. Rewrite it as a fraction. Factor out something if you can. Rewrite it as a fraction if needed. It can be creative. It can be quadratic function, anything. Second step is actually to find those points, critical numbers. So the top gives me 4 plus 5/3 x equals 0. And then I will do the bottom later. Let's solve it for x. In this case, not too bad. What do you think we should do?
So subtract the 4 over.
And it gives me -4.
And then multiply by 3.
And divide by 5. I like doing it the same step. So we're going to have -4 times 3/5, which is what?
Negative 12/5.
12/5. Good. Negative 12/5. This is my first critical number because it's a 0 for the derivative of the function. Then I want to check, always check the bottom. And the bottom says that I have x to the 1/3. And I check where x to the 1/3 can be 0. Sometimes it's not 0 at all. And we had the situation before. Here, I want to find zeros for the denominator. Well, what do you think? What x can make x to the 1/3 0?
0.
Zeros. So this is the second critical number. The first one is coming from zeros. The second one is coming from finding where the function, the derivative, is not defined. It does not exist. And now we just list them. Critical numbers. Remember, we want to find all the critical numbers. Critical numbers are x equals -12/5 and 0. Two different situations, but that's what we call critical numbers. Let's do one more example. Here, the function is given as 8x minus 7 times e to the 5x. What do you see here when you just take a glance at the function?
Products.
Exactly, I can see a product of a linear function and an exponential function. So when I'll be taking derivative of this function, and you remember step 1, take a derivative. Step 1, take a derivative all the time. Taking derivative of the function, what should I use here? There's some kind of rule I should use here.
The product rule.
Yeah, product rule. It's a product of two functions here. Depends how you learn it. Some people write it as u times v and so on. Product rule. So we should be careful here when we're taking derivative. Well, let's do it. What should go first?
So we're going to have 8x minus 7.
Good. Copy the first part times.
And then the 5e to the 5x.
Good. Which is coming from taking derivative of the second part, derivative of the exponential. When you take a derivative of the exponential, you copy the function, and then you do times the derivative of the function inside. And here you use the other rule.
The chain rule.
Chain rule, yes, good job. Chain rule. This is very important, not to make those little mistakes, because it takes you back to the previous material when you should be careful with all those little things. Plus, now what we're doing, copying which kind of function?
The 8.
So, 8 is coming from where?
The derivative of the
Derivative of the first function. Yes, good.
And then e to the 5x.
E to the 5x. Good. Product rule. And the chain rule when we did the first part. Now, if you're stuck at this moment, there's a good suggestion which I mentioned last time. Factor something out. And this is important. Don't stuck too much. You just try different ways to do it. And then with time you will have some practice, you will have some skills, and you will remember that, oh, most of the time there's something to factor out. What should we factor out in this case?
E to the 5x.
Yes, e to the 5x seems to be a good choice. Again, if it doesn't work, you just try different methods, and that's how we do it all the time. Let's factor out e to the 5x. What is going to stay then?
We're going to have 8x minus 7.
Yes, good. 8x minus 7 times
Times 5.
5 plus
8.
plus 8. Yes, excellent. Now, before moving to the step 2, which is, as you remember, we want to write down, the derivative equals 0, solve for x, and to find points where the derivative does not exist. Before doing this, let's simplify first. E to the 5x, and let's collect all the terms. 5x, 8x times 5 is
40.
40x minus 7 times 5,
35.
35, plus
8.
8. Good. Which gives me e to the 5x times 40x minus
27.
Good, 27 exactly. Now we're ready to do the second step. And the second step says, let z be equal to 0. Also, you remember two cases. So zeros, yes, we're going to solve it right now for x and find the 0. But the second case is where the function does not, where this derivative does not exist. However, e to the 5x defined for all x. 40x minus 27 defined for all x. So we will not have the second case of critical numbers. Just the first case, but you always should check both. So step 2, solving for x when I want to set my derivative to be 0. Well, you remember the product. First you want to check that the first term is 0 and then the second term is 0 and so on. But e to the 5x cannot be 0. If you don't remember, I will show you the graph. It's always positive. So it doesn't give us any solution and it doesn't give us any critical numbers here. Thus, we just need to solve the second part, which is 40x minus 27 gives me 0. Solving for x, what should we do?
Add 27.
40x equals 27.
And then divide by 40.
Divide by 40. 27 over 40. And this is my critical, the only critical number. And that's how you find critical numbers. Again, just to remind you, that was a rare example when we had infinitely many critical numbers. You will not gonna have those kind of examples. You can have two types of critical numbers coming from zeros, coming from the cases when derivative does not exist. You can have one. There are different cases here. So you just need to work this out and see what you have in the concrete case. Thank you.